Thank you for coming to my talk. Rust is a language that is widely acknowledged to be safe. Today, we're going to look at some of its performance characteristics, in particular, asynchronous Rust. I am Glauber Costa, and I'm the author of maintainer of the Rust asynchronous framework, Glommio. I am the veteran of low latency and high performance systems, and I work with high profile systems in the past, like the Linux kernel, ScyllaDB, and more recently, where I wrote Glommio, Datadog. Currently, I am the founder and CEO of Chisel Strike. Before we talk about asynchronous Rust, we need to look at what Rust is. And here I'll ask for an apology for the power users in the audience, but to level everybody up and put everybody on the same page, we need to take a quick introductory look at what Rust is to begin with. And one bird's eye view to look into that is to think of it as a less powerful C++. I mean, this analogy does break down at some point, but it's a good way to get started. This is a weird statement to make because usually we want our languages to be powerful. We want our languages to be expressive. And now here Glauber comes saying that Rust is a less powerful C++. But what happens when you give power to the writer of the code is that you immediately take away power from the reader of the code, be it a person or the compiler, that now cannot assume things that it would otherwise will be able to. One example of that are smart pointers. C++ obviously has smart pointers. You can have unique pointers, shared pointers, and they're all safe. But at the same time, you can get a naked pointer that points to the same location and do whatever you want with that. Again, more powerful. In Rust, you can only do this if you use the unsafe keyword. And in practice, you end up not doing so. I can share at this point like an anecdotal story. Obviously, I've been writing Rust professionally for almost 2 years now. And I had to fight essentially 2 memory bugs that I can remember of invalid memory accesses. In C++, this is essentially a slow Wednesday. So in practice, that does work. Whenever you do something that breaks that safety in Rust, you need to be very careful. You need to mark it as unsafe. And as long as you're not using any unsafe construct, everything is safe. That allows us to establish a concept of lifetimes. So because everything in Rust follows the pattern of resource acquisition is initialization, or RAI, you can define the lifetime of an object very clearly. An object gets to be alive when it's created, and once it goes out of scope, it is destroyed. The compiler then can look at those lifetimes and make sure that any reference to this object does not outlive the original object. This is called the borrow checker. So in the code example that you're seeing here, we create an object, then we get a reference to this object, and then we drop the original object. The compiler itself, at compile time, will not allow this code to compile. Note that you can still have circular references that prevents those objects to be destroyed, so memory leaks are possible, but not invalid memory accesses. Rust also has a powerful trait system, which is fairly similar to C++ concepts. You can specify a generic type, but you don't necessarily use this generic type without telling the system what do you expect from it. So in the example in the left, if we just pass something of type T and then we try to print it, it will fail because I don't know, the compiler doesn't know that this is something that can be printed. On the right, we actually specify that my type implements the trait display. Now I know that this type has a function that allows it to be transformed into a string. Traits and lifetimes play very well together. You can also specify lifetimes as part of those trait bounds. And one of them is special. That is the static lifetime. The static lifetime essentially means it's guaranteed to be alive. When we're talking about a reference, that means that we're talking about something that is a statically defined string or a statically defined object. It is by definition alive throughout the entire lifetime of the program. But when it's used as a trait bound, it can also mean something that's not a reference at all. So if something is not a reference at all, it is just owned, it is by definition guaranteed to be alive throughout the execution of this function. So you can see the example here. I essentially have one variable. We pass that variable. You can pass A to background. You cannot pass a reference because, again, that reference now has a lifetime that is shorter than the entire lifetime of the program. How do we deal with references in static context? So if something requires a static bound and we want to pass something that is shared, that is very complex. We only really have two good alternatives. One of them is to essentially have something that, again, is alive throughout the entire lifetime of the program. And the other one is to pass something that is owned. So you end up passing a share pointer instead, right? So the share pointer, the object itself is not a reference. The pointee is kept alive through the references that the owned objects sustain. So every time you do this, remember, leaks are still possible because it might be that you hold on to one of those share pointers and never release it, but memory leaks are not because the share pointer guaranteed that the lifetime is essentially extended. Those share pointers are not atomic, by the way, right? So they don't impose too much of a performance cost, but that is the way we usually handle static lifetimes in those contexts. However, things that have to be passed across multiple threads, they do require a special trait. That trait is called send. So in the previous example, if you have a share pointer and that share pointer is not atomic, obviously it is not safe to send to a different thread because when the other thread will try to manipulate the reference count, it will break. That means that you cannot pass that to a different thread at all. If you want to do that, there is another type, a special kind of reference counted pointer called ARC, or atomic reference count, that implements the send trait, the send trait bound. So you can pass something that is an ARC to multiple threads, but you cannot pass something that is a simple RC. Again, because it is not safe to be shared across threads, the trait system expresses that. Async Rust, now getting to Async Rust finally, is essentially implemented on top of the trait system. Any object in Rust can be made into a future. You essentially get your object to implement the future trait, and you have an output, something that this future will output. You have a context, which is it's entirely within the domain of the executor. It's managed by the executor. And every time you call this poll function, it returns either ready or pending. You can also have a function that you mark as async, and then Rust will auto-generate something like that for you. But under the hood, it's all implementing the future trait. However, Rust does not specify how to execute those futures. It just gives you the trait. Driving the futures by itself is the task of the executor. There is no standard executor in Rust. You're supposed to bring your own. And the most famous by far is Tokio. There is a second contender that is async std, and Glommio, which is a very niche thread per core executor using IOU ring. We're going to talk more about it in a few. The executor is supposed to just call your poll function continuously, but in practice, it's much more than that. To even make those functions ready, the executor has to be responsible for doing I/O, for managing timers, implementing channels. So very quickly, they can become quite complex. Tokio in particular, and also Glommio, they are quite complex. Rust also, by default, doesn't have any parallelism. So in this example here, we have two things that we're calling await on. That's how you essentially use that as a user. You're using now your async code. Foo await and bar await, those things do not execute at the same time. They execute concurrently as they would, for example, on a coroutine. If you want to drive parallelism, there are select-like mechanisms in which you can pass a lot of futures and it will create an internal list. But more often than not, the executor provides you with a spawn function. That spawn function allows you to spawn a future that starts executing more or less immediately, and you can await later. So to drive parallelism, the executor ends up being involved. Now, that poses a problem. Once you spawn something that will run in the background, that you may or may not await, by the way, the lifetimes become quite complex. It is now almost impossible to guarantee that the lifetime of the references that you're passing to this future are going to be alive. So you end up having to specify an static bound, meaning now you're dealing with things that are alive statically or share pointers. But Tokio in particular, because it is a multi-threaded executor, those futures can be polled in different times from different threads. So it does require the send trade. So if you look at the spawn function, the signature of the spawn function in Tokio, for example, you will see that this requires send and static. And this being a conference of latency-minded people, I guess you can all already anticipate what the problem with that is. Glommio, on the other hand, has the same lifetime problem. There's no magic here. Those lifetimes become arbitrary. But because we are a thread per core executor, you don't have to specify the send bound, meaning you can actually start passing share pointers that are not atomic to Glommio futures. To do that, of course, because those futures are moving to different threads in the case of Tokio, not only your futures now have to have a lot of atomics, but the entire state machine of the executor has to have atomics as well. Glommio, on the other hand, is almost completely free of atomics. And I say almost because there is one case in which we are not. It is possible, of course, to have a channel that connects two executors. So you're going to do a little bit of work in one executor and the rest of the work in another executor and communicate through message passing. If we were just manipulating the state machine from those two executors, we would need atomics. But what we do instead is that the reference count that keeps the task alive is atomic. So if you're not doing this cross executor, it's a relaxed atomic, it's pretty cheap. And if you are doing this across more than one executor, only the executors that are dealing with this task, which tend to be just two, are involved. And when you actually need to wake this task, meaning that now you have to act on the state machine, you do it locally. So each executor has its own internal queue in which we pass those wake requests back to the original executor. That guarantees that we are essentially free of atomics in the state machine as well. The results of that should be unsurprising for this audience. This is a third-party benchmark. You're welcome to take a deeper look. And what it's trying to do is create a gRPC server and increase the number of clients until the point of saturation. And this is a comparison between Glommio, Tokio, Async STD, and another one that is a very small executor called Small. What you're going to see here is that in the beginning, there isn't really a lot of performance difference between those executors. But all the other executors that are multi-threaded, very early on, they're showing signs of contention, while Glommio essentially keeps going linearly until saturation. The unfortunate reality is that Rust sells us an image that it should be trivial, or at least very easy, to swap these executors. It's not like that. There are a couple of very specific problems that are solvable in the near future. I believe, for example, the lack of a timer trait and even the lack of a spawn trait. So you end up registering a timer and spawning functions become quite executor specific. But also, unfortunately, the send trait is quite viral because once your spawn function requires it, anything that you will ever potentially spawn has to be safe send as well. So you look at the libraries that are built around Tokio, they require send in many more places than it would be reasonable. So that was one of the problems of swapping executors. Another big challenge with performance of Rust, asynchronous Rust in particular, is essentially just file I/O. Tokio file I/O uses a thread pool underneath. If you're talking about very fast devices, if you're talking about devices like the Intel Optane, for example, and I recently wrote a blog post about it, those devices have latencies in dozens of microseconds, sometimes even single-digit microsecond. So if you're doing a context switch every time you need to do I/O, your performance is not going to be the best. Linux I/O is one way to do it, to get it, but it's very hard to get it right. The folks at Scylla had done a great job at getting it right, but it's not for everybody. I/O ring is what is promised to essentially bring this to the masses. So there is a comparison table here that I wrote in a recent blog between all of those methods of doing I/O, and you will see that a thread pool for very fast devices really doesn't work that well. Async I/O, Linux I/O and I/O ring, very similar performance. I/O ring is just a lot saner to use. So again, Glommio does pack I/O ring as well, which is one of the ways we're trying to solve this problem with File I/O. So Glommio File I/O, we use I/O ring natively. We incentivize direct I/O, but we don't require it. And again, that is because I/O ring is very good with asynchronous I/O of any kind. We also support positional reads that the Rust file traits don't. Rust file traits are very sequential in nature, right? They're focused on streams. So if you want to do positional reads, you have to seek and stream. Glommio natively supports read at. And I/O ring also allows us to pre-map register buffers that make direct I/O even faster. And we do implement streams as well, using all of the standard traits in Rust. Newer developments, it was recently announced that Tokio is pursuing something called Tokio I/O ring. So they're inspired by Glommio's architecture, trying to bring a lot of those concepts into Tokio. And ultimately, I think this will benefit the community a lot. I do wish them well, but the situation as of today, unfortunately, is as I described. Another final problem is with buffer lifetimes. It is very hard in Rust to do zero copy and work with any interface in which you aspire to do zero copy. The reason for that is the infamous, at least to people versed on it, cancellation problem. What happens with that is that whenever you have a task, this task can essentially go out of scope and be canceled at any time. So if you had a buffer that you passed to the kernel to do zero copy on it through, for example, direct I/O on I/O ring, when the task is canceled, the kernel will still try to write to this buffer or read into this buffer, but the task is no longer there. The memory, this becomes unsafe. The poll read trait, the poll read method in the stream reader traits gets a buffer. But again, we cannot pass this buffer directly to the kernel. There is another trait that is supposed to solve this problem, the Async BufRead. This trait is supposed to be used for things that manage their own buffer internally. So things like I/O ring that have their own buffers that they can map to, and only then we will read from it. This trait goes in the right direction, but you are usually not calling those functions directly. You're not calling poll read. You're not calling fuel buffer. That's not usually how users consume that. They usually consume it through higher level functions that exist in a different trait. In this case, for example, it's usually async BufRead extended or async BufRead ext. Those are the collection of functions that deal with types that implement that trait. Those functions all essentially have a buffer in which you expect your data to arrive. So even if the trait itself is not preventing you from doing zero copy, that last layer, if you really want to use the expressiveness and the power of those existing libraries and Rust traits, zero copy becomes very hard. The summary of the presentation, reference count explosion unfortunately limits the scalability of what asynchronous Rust can do. Because of the lifetimes, you have to sprinkle reference counts everywhere, and obviously that has a performance impact. It is possible to avoid this with a thread per core executor, but currently it's very hard to swap executors. File I/O performance is a concern. I/O ring increased adoption will help mitigate that. Tokio has exciting news in that front, and we're waiting to hear more. It's also still very hard to do zero copy. The async workgroup, though, has a lot of good proposals on how to handle this problem, and I'm hoping to see a lot of exciting news in the future. And if you want to get in touch with me, just feel free to either shoot me an email or a message on Twitter, and have a great day.